Okay, what do we want to do with this first equation? Yeah, it looks like the nitrogen monoxide and the oxygens are on the correct side, so we multiply the whole thing by 2. Then we have the correct number of nitrogen monoxides, so we'll multiply it by 2. We'll leave the orientation the same. The next one. Yeah, okay, so we'll go 4 and NH3 turns into that. Put a 2 right there, put a 6 right here. And we'll get rid of all this. So this sign goes to a positive, and then we multiply this one by 2. And the last one, multiply by 3. But leave it where it is. Oh. So this becomes a 6. So we get our 6 water molecules. This becomes 3 oxygen, and this becomes 6 hydrogen. So I've got to multiply by 3. Let's see. All right, so there are my 6 water molecules. There are my 6 water molecules. There are my 4 nitrogen monoxides. 4 nitrogen monoxides. Let's see, I've got 2 and 3 oxygens. So there's my 5 oxygens. And then I've got my 4 ammonias, and there are my 4 ammonias. Let's make sure we got everything to cancel out. Here are 6 H2s, and here are 6 H2s on the other side of the arrow, so they're gone. And then here are 2 N2s, and here are 2 N2s, so those guys cancel out. So we're good. All right. So I've got negative 180.5 times 2 plus 91.8 times 2 plus negative 483.6 times 3. So I get negative 16 to 8.2 kilojoules per mole. Okay. Can anybody talk about this reaction? What type of reaction this is? Going back to 121. Your reaction types were combination, decomposition, single replacement, double replacement, combustion. Yeah, there's an oxygen here. So what is the oxygen burning? Ammonia, which is highly flammable. As long as it's like dissolved in water and Windex, it's not a problem, but ammonia gas is very, very flammable. And so this makes sense, right? This big number, this negative big number is producing a lot of heat during this course of this reaction. This is something that would happen if you burn fertilizer. All right. Atoms with the following hybridizations form bonds with how many different atoms and what shape? All right. So the first one, how many different things does an sp3 carbon form bonds with? 4 things. And so what's its shape? Tetrahedral. All right. And sp2? 3. And its shape? Trigonal plane. And the sp? 2. So I want us to realize that the S's are all have like a one subscript, superscript, and then this P that doesn't have anything has a one superscript. So that's where I get 2 from, that's where I get 3 from, and that's where I get 4 from. You just add the exponents like you were multiplying the same base number with exponents, like 2 to the third times 2 to the fourth. It would just be 2 to the seventh. All right, look up 3-hexene, draw it here. How many sigma bonds, pi bonds in this molecule? All right, so what's that hex prefix mean? 6. And then did you guys figure out what the ene suffix meant? This is really something for next quarter, but ene means a double bond within an organic molecule. So the 6 refers to 6 carbons, and then the ene means a double bond, and the 3 means between starting at carbon number 3. Doesn't matter what side you count from. People, just because it's English, usually start on the left side. So 1, 2, 3. So going from carbon number 3 to carbon number 4, that would be 3-hexene. And what I haven't drawn are the hydrogens. Oops. Okay. So all those lines with nothing on them, those are lines going to hydrogens. And then on Monday, I put up that drawing of heme, right? And then I told you about the lazier way to draw out the molecule. And so the lazy way to draw this would be that. And so what you're looking at is, this is a carbon, 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 carbon. And anywhere you don't see anything attached to the carbon, besides another carbon, are hydrogens, getting it up to 4. So how many H's are right here? 3. And that's what these spots are here. Those are 3 H's. And then the other side, same situation, 3 H's there. This one has 2 H's on it because it's connected to 2 carbons, and then those are H's. So that's what this spot and this spot here are, this one and this one. And then this situation, it's got only 1 hydrogen on it because it's connected to that carbon once and that carbon twice. So it can only have 1 H on it. Same situation with this guy. All right, so hybridization. What is the hybridization for, say, this one right here? Yeah, it's connected to a hydrogen, and a hydrogen, and a carbon. So that's sp3. What about this one? Same. It's connected to 2 carbons and 2 hydrogens, but it's still connected to 4 things. So your sp3, what about this one here? Same. This one here? Same. So these ones, these guys are all sp3. And then what about these two? sp2. They're both sp2 because they're only connected to 3 things. So carbon, carbon, hydrogen. So that makes them sp3. And the other p orbital that we're not talking about is being used to make the double bond between those 2 carbons. Shapes. Around all the sp3s, what's the shape? Tetrahedral. And then around the sp2s, trigonal planar. So this does still look jagged. It would be like an up-down situation. And then the only interesting thing about this molecule, besides the double bond being super reactive, is because there's a double bond here, that means this part right here and this part right here can't rotate. There's a fixed position there. This hydrogen here can just free form spin. This one here can just free form spin. They can spin relative to each other. But when I get between these 2 carbons, they're in a fixed position. Spinnable, spinnable, fixed, fixed, and then those last 2 spinnable. Okay. What was the reason that the oxygen was able to interact with the magnetic field?
It's valence electrons don't have ones that need to come in the field, so they, yeah, you get the field.
There are two electrons in the same molecular orbital, which actually would be this one here. And they're only one in each of those orbitals, molecular orbitals, and they're both spinning in the same direction. So because they're both spinning in the same direction, I get a north and a south and a north and a south. So there's a magnetic field can interact with this larger north-south. And that's not going to happen with this nitrogen that we're going to draw here in a second.
They're creating like a tiny field.
They're creating a really tiny magnetic field, but it's not a magnetic field that's strong enough to like stick to something that isn't a magnet. It will be influenced by a magnetic field, but it's not going to be doing any influencing. It's too weak. All right, so let me make this smaller. This up a little bit. All right, so we're talking about nitrogen, and so nitrogen has 7 total electrons. 2 of them are in the 1s2; those aren't going to be drawn, and so then the other 5, I've got 1 here, 1 there, 1 here, 1 here, 1 here, because of Hund's rule, where we put 1 electron in each orbital before doubling up. All right, so here's my 1 nitrogen on this side, here's my other nitrogen on this side, and they're going to come together to form this molecular orbital. We just take the electrons and fill them on the way up. So I have 1 electron from here, 1 there, and so I form a bond or a pair, the molecular orbital. So those 4 electrons are we take care of, and then I put 1 down, 1 up, and then same situation here. All right, so I've used up all 5 of my available valence electrons, and we end up having those and those. So that's 8 bonding electrons. And then I've got these, which is 2 anti-bond electrons. So that leaves me with 6 bonding electrons. So 6 bonding electrons equals how many covalent bonds? 3. Each covalent bond is required 1 electron from each, or at least a pair of electrons to go in to form that bond. And so that would lead us to believe that the nitrogen will form a triple bond, which it does. That's it. Anybody have any questions about this? Ryan, do you have any questions?
No, I'm good.
Okay.